As we consider a modern-day switch, let's think back to the 1980s. Back in the 1980s, that's when Ethernet bridges came out. Back in the 80s, networks were relatively slow. Implementations of Ethernet were 10 base 2 or 10 base 5 typically, and bridges were developed to limit collision domains. This allowed networks to scale somewhat. You could have a collection of hubs on either side of a two-port bridge, as an example, and collisions seen on one side would not impact traffic on the other side. Architecturally, bridges worked a lot like computers of the day. If you had a Unix workstation, it might be using a RISC processor, or you might be using a computer that had a CISC processor. CISC, by the way, is complex instruction set computing. RISC is reduced instruction set computing. The bottom line is, frame forwarding decisions were made in software, and as a result, this frame forwarding was relatively slow compared to what we have today. The big change came in the 1990s with the introduction of switches. And on screen we see the Cisco Catalyst 3750 series of switches. In the 1990s, even though these particular switches were not available in the 1990s. But in the 1990s, with the introduction of switches, we started to have relatively fast networks. I personally remember different vendors coming into my office and explaining how architecturally their model of switch was better than a competitor's model of switch. And we had all kinds of discussions about interframe gap times and how frames were forwarded. But in reality, they all approached wire speed. They were all very, very fast. And that was largely due to having ASICs, application-specific integrated circuits, chips built into the Ethernet switch that made the frame forwarding decisions. No longer did we have to rely on a software program, essentially, running on a CISC or RISC processor. No, now we had dedicated circuitry that was in charge of making those forwarding decisions. And switches, like bridges, they limit collision domains. But one of the big advantages besides speed is, as you can see on screen, switches tend to have a much higher port density than bridges. You have a much lower cost per port when it comes to an Ethernet switch as compared to an Ethernet bridge. And the topic we want to discuss over our next few slides is frame forwarding. We've got different frame forwarding options. In other words, when a frame comes into one of those Ethernet switch ports, when does that switch begin to forward the frame out of the egress, out of the outgoing port? One approach we're going to discuss is cut-through switching. We're going to contrast that with store and forward switching. And a third type, which is really sort of a compromise between the two, is something called fragment-free switching. Let's begin our discussion with cut-through switching.